Okay, so in this video, we'll be doing some more exercises on language operations. So in this exercise, we're given the fact that we have two languages, L1 and L2 over the alphabet AB. And essentially what we want to do is find particular examples for L1 and L2. So set L1 and L2 to particular languages such that um, we can satisfy each of these sentences. That sentence in English is a bit ambiguous. What I mean is I find an L1 and L2 such that this one works. Then I find a potentially different one, different L1 and L2 such that this one works, and so on. If it was find an L1 and L2 such that all of these work, then yeah, that's a lot more difficult. I actually think it's still possible, but it's a bit more tricky. So, like I said, let's do this one by one. Let's try for each statement to find L1 and L2 such that the statement is satisfied. So the first statement is that L1 power 0 is equal to the language containing the empty string. Well, this is just by definition, right? So this is true by definition. By definition. So any language you pick will work. You pick will work. Something that's maybe not intuitive is even if you pick the empty set. So even if you said L1 is the language that doesn't contain any strings, then, well, I mean, it's a language, right? It's a subset of sigma star. And so by definition, that means that if you power it to the zero, then it returns the language containing the empty string and only the empty string. Okay, so that was not that bad. Let's look at number two. So number two, I want to find L1 and L2 such that L1 union L1 square. Well, the cardinality or the size of L1 union L1 square is equal to the cardinality of L1 plus the cardinality of L1 whole squared. So this is definitely not true in general. So for instance, if you just had said that L1 was the language containing the empty string, then L1 square is also just a language that contains the empty string. And so L1 union L1 square, that's also just a language that contains the empty string. So the size of this guy is 1, but then the size of each of these um, are 1. And so together as a sum, it's 2. And so, of course, that means that in general, the statement is not true. But how can we find a particular setting such that it is true? Well, essentially, you kind of have to try to avoid a language that contains the empty string. Because if you get a language that contains the empty string, then you're going to get overlap between L1 square and L1, right? So if, so this is maybe just a note, if the empty string is in L1, then you'll have overlap uh, between L1 and L1 square. Namely, you'll actually have all of L1 in L1 square because you'll take the empty string, right? So you'll take the empty string from this first L1, and then you'll concatenate it with all of L1 again. So then you'll just get all of L1. And the reason why that's a problem is because because sets do not allow duplicates, you'll remove all the duplicates. And then that might cause a problem when you try to see if it's equal to this guy. So that's one thing that we definitely have to avoid is something that contains the empty string. So let's try something easy. Let's see if this works. If I just have L1 is the singleton that just contains A, right? Well, in that case, L1 square is A square, and then L1 union L1 square. Well, there are no duplicates, so I'm just going to add each of these to the set. And then the size of this, right? The size of this is 2. and the size of each of these is 1. And so we do get that the sum of the sizes of each of these languages is equal to the size of this language. So that works. Nice. And so that's how we satisfy number 2. Number three, number 3 says, okay, so we want that L1 is a subset of L2, and we also want that L1 concat L2 is equal to L2 concat L1. So this is definitely not true in general. So language, just like string concatenation, is not commutative. So you can't commute, you can't swap L1 and L2 and just assume that you'll get the same thing. Like for instance, if you had the language, the singleton languages A and B, then if you concatenate them together, that's AB. And this is definitely not the same as BA, which is what you would get if you swap these guys, right? Okay, but now I actually want it to work. So let's see. I think what we probably want to do is we know that if we have the language that contains the empty string. So by the way, the language that contains the empty string, that's always a nice language to always keep in mind if you're trying to satisfy or trying to find like an edge case. This is usually a good one. So I know that if I do this with L, then it's the same as doing L with this because it's just L. So then, okay, why don't I just define L2 as the empty string and then A, and then L1 as the empty string. So I satisfy the first condition, L1 is a subset of L2. And I also satisfy the second condition, right? Because of what I just said here. So L1 concat L2, that's going to be empty string L2. So that's the same as L2 empty string. And so that's the same as L2 L1. And so that satisfies both of the conditions. So that works for 3. 4 says L1 concat L2 is L1. Okay, so 4 says L1 concat L2, that's L1. This is also definitely not true in general, right? Like what if you have like here A power n and here you have B power n? Well, together this is going to be A power n, B power m, but here you just have A power n, right? So that's not going to work. So I could actually again use the singleton language containing the empty string. I'm going to use a different one because this is also a useful language to have if you want to think of edge cases. Suppose you take L1 as the empty set. Okay, so L1 is the empty set, and actually L2 is any language. Okay, well, what is L1 concat L2? Well, to do L1 concat L2, what do you have to do? You have to do for every string in L1 and for every string in L2, right? So if this was a for loop, then you do something like suppose X represents L1 concat L2, then you have to do for W in L1, for U in L2, append WU to X, right? And then return X. Okay, but hopefully what you see is that this for loop doesn't iterate over anything, right? So you do for W in the empty set. Well, that's just saying for I from 2 to 1 or something crazy, right? Or like for I in an empty array, right? So 2 to 1 was maybe not the best choice, but for I in an empty array, well, I mean, the for loop is going to execute, it's going to execute 0 times. So then this is never going to execute because I'm never actually going to go into the body of the for loop. And so this is going to remain empty, right? So that means that L1 concat L2 is also going to remain empty because, I mean, it's the logic transfers, right? And so I get that L1 is the same as L1 concat L2 because I use this um, albeit cheap trick, but trick nonetheless, that allows me to say that the two languages are the same. Okay, let's look at the last one. V L1 concat L2 is the same as L1 cross product L2. So again, this is not going to be true in general. Why is this not going to be true in general? For instance, um, if I had a string, right? So if I had something like uh, A and then, so I had the empty string and then A, and then let's say the empty string and then A. You know what? I don't even like without the empty string. So just so that I convince you that I'm not using like a cheap pad. And let's just do A. Is this gonna work? No. Um, oh, this is gonna work. Okay, nice. Okay, so if I have L1 and L2, right? L1 is A, B, and L2 is A and B. Then what's the result? Well, A concatenate with A, that's A squared. A with B, that's AB. AB with ABA, that's ABA. No, actually, this is not going to work. And then AB with B, AB with B, that's AB squared. Okay. Well, okay, so this is going to be an example where I actually do satisfy it. So the length of this or the size of this is 4. And then the cardinality of the cross product, that's always going to be the cardinality of the first set times the cardinality of the second set. So um, L1 cross L2, let's just write it here, A and AB. Well, that's going to be A. So I'm going to create tuples, right? In particular, I'm going to create tuples of size 2. The first element is going to always be a string from L1. The second element is always going to be a string from L2. So I'm going to get A. It's going to be coupled with A. Also, A is going to be coupled with B. AB is going to be coupled with A. And then AB is also going to be coupled with B. Okay, and so you see that the cardinality of this is the same as the cardinality of this is 4. So this is an example for which we actually do satisfy. Okay, so what about one where it doesn't work? I just want to convince you that it actually doesn't work in general. And I kind of don't want to use this hacky trick of like maybe the empty string or the empty set. So let's see. I think if we do something like the idea is you kind of, for it not to be satisfied, is you kind of want some duplication of a string to happen. So for instance, what are the ways in which I can create the string ABB? I can have, two sets, right? Where maybe A is here and then BB is here. So that's one way of creating ABB, but there's also AB and then B. So there's AB and then B. So if we concatenate this together, then I'll get A with a BB, so ABB, A with B, so AB, AB with BB, so ABQ, and then AB with B, so ABB. Okay, so then I get duplicates, right? So I remove one, and so actually the size of this language is 3. But if I had done this with the cross product, I'd done this with the cross product, then I would have gotten something like A, B in a tuple, A and B also in a tuple, AB and BB also in a tuple, AB and B also in a tuple. So then here, this gives me size 4. So you can kind of see that like the tuples, they do kind of represent strings, but they give you a bit extra information, right? So here they tell you in particular, this is like the string ABBB. It's like the string ABQ, but in particular, it also tells you the source of each of the substrings of the string. So in particular, that the first part of the string AB comes from one language and the second part comes from another language. So because you have like this extra information, then that's what creates this uniqueness. So that's why you don't actually have duplication. Okay, and so I think altogether, right, we just had five, right? Altogether, this solves this exercise as well.